In question 6, for a plane transmission diffraction grating, the grating equation for the first order beam is given by lambda equals d sine theta. In A, we have a diagram something like this, and we need to label the distances lowercase d and lambda. Well, the distance between the slits here is d, and the wavelength is given by this dimension here, which is lambda. In B, we need to state and explain what will happen to the value of the angle theta for the first order beam if the wavelength of the light is reduced. Well, if the wavelength decreases, the angle will decrease. This is because at a smaller wavelength, a smaller path difference is needed to get constructive interference for the first order maximum. In C, we have the line spectrum from star X and the spectra from several elements. We need to pick which 3 elements are present in the atmosphere of X. We're looking for elements where the lines line up with those from star X, and these are mercury, helium, and hydrogen. In D, we're told the diffraction grating used to obtain the spectrum of X had 300 lines per millimeter. In part 1, we need to find the distance between the centers of 2 adjacent slits on this grating. Well, there are 300 lines per millimeter, so 300,000 lines per meter. The distance between the lines will be 1 meter divided by 300,000, which is 3.3 times 10 to the minus 6 meters. In part 2, we need to find the first order angle of diffraction of line P in figure 7, which has a wavelength of 550 nanometers. Well, we're given n lambda equals d sine theta, and in this case n equals 1 for the first order maximum. So sine theta equals n lambda over d, which is 1 times the wavelength 550 nanometers over the separation of the slits we found in the previous part of the question, gives sine theta at 0.165, and theta then is 9.5 degrees.